I don't know what to do now. I am just stuck. And no simple algebra move is going to help me here. I can't multiply by the conjugate. I have no common denominators. I have no simple tricky factoring, things like that, right? This is like actually like a deep problem. And so this limit definition is it's sort of good when I already know what's going on, but it's not a good way to kind of discover or understand what the derivative of a product is. You guys with me? All right, so let's pause this and let's pivot to deep understanding. So deep understanding, let's not try to prove something until we even know what it is that we're proving. That's the better way to do mathematics. First, play around, and then once you know the answer, then go prove it. All right. Well, what does it even mean to take the derivative of the product of two functions? You might be asking. What does even the derivative mean? And what does the product of two functions even mean? Okay, so we need to answer all these questions. Well, okay, what does the derivative mean? As I already said, we have this kind of very flexible, hopefully by this point already have this very deep and flexible understanding of differentiation. It's over the tangent line to the curve, it's instantaneous rate of change. It's the change in the function given an infinite amount of time, right? You give me an infinite, tiny bit of change along the x-axis, then how much the function grows, that's basically the derivative. Okay, well, before I even talk about the derivative of the product of two functions, I should talk about what is the product of two functions. After all, we're not in the habit so often of multiplying two functions. Let's try to start with like a word problem. Let's try to understand what the product of two functions even means. Okay, so I made this example. We have a toy factory. Let's go. This toy factory is very big. It is running around the clock, 24 hours a day, producing like toys. All right, and it's one of these like massive factories that you see in like whatever, like in Taiwan or something. It just takes up like like a mile by a mile, and there's like millions of people in there just working away making toys. So we also have a workforce, and the workforce is very flexible because people are not just working 9 to 5. People are working like all the time. Like, so some people work 9 to 5, but other people work in the evening. Some people work in the middle of the night. And so the number of workers at the factory at any given time is fluctuating. So let's invent this function W, and let's let W be the number of workers in the factory at a certain time, where T is, who knows, minutes, hours, or something like that, throughout the day. Okay, so this function is going up and down. It's going up as people are entering. It's going down as people are leaving. Great. Okay, then there are these other sort of factors which might influence how efficient this factory is at any given time at producing toys. And what could it control the efficiency? Well, many things. Maybe at a certain time of day, people are kind of sleepy or something and they work slower. Maybe the amount of electricity available to the company is changing based on the local conditions. And so when there's a lot of electricity available, suddenly the engines will run much faster. You can produce more toys. Maybe the factory is solar powered, so during the day, we're more efficient or whatever. Okay, so let's define this function E and let it be measured in number of toys produced per worker per hour. So it's the general efficiency of the factory measured as number of toys produced per worker per hour. Who's with me? Okay, this is also going up and going down based on the time of day. Okay, well now we get to our sort of first question. All right, what is, sort of in words now, what is W prime? Like articulate that, like what it is measuring.
The rate of change of the number of workers?
Yeah, the rate of change of the number of workers. Okay, so that is, of course, correct. The rate of change of the number of workers. And it's actually probably the most precise way of answering these kind of questions is just putting the rate of change of in front of the function that you're differentiating. You can't go wrong with that. But sort of, can you speak kind of more casually and more loosely? Sort of what is it kind of telling you? Like, what if it's really big? What does that mean? If W prime of T is really big at a certain time, then finish that sentence.
There's a big migration of workers in or out of the company.
Yeah, specifically in, right? Yeah. Yeah. So yeah, if W prime, it is the rate of change of the number of workers, but it's the sort of it's the change in the number of workers over some infinitesimal amount of time. And so it's measuring sort of the rate at which the workers are arriving. And so basically, if W prime is big, then it means that at that moment, a lot of workers are arriving to the factory. Okay, so for example, if most people primarily do work 9 to 5 at this factory, then if you ask for W prime at 9 a.m., it's going to be huge because 9 a.m. many people are arriving. And so the rate at which the workers are arriving is very big. Okay, so at any given moment, tons of workers are coming. Okay, that one was pretty easy. What is E prime? Well, it's the rate of change of efficiency. Okay, so okay, yeah, like I said, you can't go wrong with just adding the rate of change of in front of the thing. Okay, but now more sort of using more sort of normal human language. What is it sort of telling you?
To get a new toy making machine.
Say it again.
To get another toy making machine.
To get another toy making machine. So they make more toys. Yeah, something like that. Okay, yeah. So efficiency is like how good each worker is at that moment at making toys, right? So like we said, if the factory depends on some kind of giant massive engine and the supply of energy is somehow low, then the machine is going to move kind of slowly. But if the machine moves quickly, then it's going to be moving quicker. So that's what the efficiency is measuring. So E prime is measuring the sort of change in efficiency. Okay, so this is like, what if like everyone after lunch, drinks a giant cup of coffee, say, right? If everyone after lunch drinks a giant cup of coffee, then suddenly everyone's efficient, everyone's going to work way faster. Suddenly everyone's efficiency is going to go way up, right? And conversely, if it's sort of a time of the day when everyone's getting kind of sleepy or whatever, maybe then the efficiency is going to go down. So if E is a big positive number, then it means everyone is getting much more efficient at that moment. And if E prime is a small positive number, it means people are just getting a little bit more efficient. If E prime is 0, it means that the efficiency is not changing. If E prime is negative, it means the efficiency is going down, right? So that would be like some rolling blackout kind of situation or whatever, where you had reduced electricity maybe in the middle of the night or something. Okay, all right. Well, so this is a good exploration of the concept of differentiation. Well, okay, let's push on. What is the product of the W and E function? So this is like the WE function, which is defined to be this. What is that measuring?
I guess the total productivity of the factory, not accounting for workers.
Yeah, I like how he says that. It's the total productivity of the factory. In other words, someone else? Yeah, what are the units?
Toys.
Toys. If you multiply number of workers by number of toys produced per worker per hour, then yeah, Autumn, are you adding on to what he's saying? So you're saying toys per hour. Yeah, so it's the number of toys produced per hour by the factory, And so what we're sort of measuring here is just like the total kind of product. It's perfect. It's perfectly answered. It's the productivity of the factory. It's the number of toys the overall factory is producing per hour. Okay, so finally, we get to the last question. What is the derivative of the product of these two functions? What is that measuring? All right, well, it's just the rate of change of the productivity, right? So it's the rate of change of the productivity of the entire factory. So it's measuring at any given time whether the factory is producing more toys per hour at that moment or fewer toys per hour. Okay. All right. So now I want to sort of ask intuitively, what should this depend on? What quantities already present in this problem should we expect to like appear in an analysis of this derivative? Well, okay. One thing that I think makes sense to expect is that this is going to depend somehow on W prime. After all, what is W prime? W prime is the rate at which workers are arriving. So if tons of workers are arriving, so that W prime is very large, then so many workers are arriving, well, that's going to change the overall productivity of the factory, right? Because the more workers that are there, the more toys are going to be produced by the factory at that moment. But no, that's true. It is going to depend on W prime. Andrew, why are you shaking your head?
Well, because the more workers arrive, the lower the efficiency value is going to be.
Well, not necessarily. Not necessarily. If it's a good factory, but you're also right that efficiency matters. So wait, hold on a second. So W prime is going to matter. I think it's got to depend on that, right? If suddenly a new 1,000 workers just arrived at the factory, then the overall productivity of the factory is going to go up. Okay, it's not obvious exactly how, but somehow. Okay, but also E prime is relevant because if suddenly everyone in the entire factory drinks a cup of coffee, it becomes more efficient. Or if the sudden electricity input available to the factory suddenly goes up, then the whole factory is going to produce more toys at that moment. Okay, but what's not so obvious is that another factor, and this might have been what Andrew was talking about, sort of, is that actually the number of workers at the factory at that moment also is relevant. Because if the efficiency suddenly goes way, way up, but there aren't enough workers there to like absorb that efficiency, then that's not going to have that much of an effect on the overall output of the factory. In other words, if there are only 10 workers at the factory and suddenly every worker becomes twice as efficient, that's only going to have a small effect on the overall output of the factory. Whereas if there are 10,000 workers at the plant and they become even 1% more efficient, that's going to have a bigger overall output effect on the output. And finally, the efficiency itself is going to matter as well, because if suddenly a huge number of workers arrive, but those workers aren't being very efficient right now, I think this is what Andrew was talking about, then that's not going to have that much of an effect. If the efficiency of the factory is very, very low, then even with additional thousands of workers, they're all going to be, relatively speaking, inefficient. And so you're not going to get that much output. But if the efficiency is high, then the change in the number of workers is going to sort of become a change in the overall output of the factory. Okay, and you could even guess right now, I bet. I've had students guess at this moment who hadn't already read the book or anything, what the rule should be. Does anyone want to just like type it in the chat right now? What do you think, based on just this discussion? Do you think maybe the formula should be to find the derivative of the product of W and E? Someone just guessed it last third period based on this conversation. Okay, well, let's keep going. Now that we understand what we're doing, maybe we should get to it, right? And okay, here it is. We're going to do this by picture. This is the other way of, so one approach to, sorry, this whole slide just looks like crap. Didn't want to do that. So what's it called? The one way of discovering the product rule is via this word problem. Another way of discovering the product rule is thinking about another way of sort of representing products. Even going all the way back to elementary school and middle school, hopefully, you are encouraged to think about multiplication via the area model. We did this on the first day of this class, right? The product of two numbers can be interpreted as the area of the rectangle whose side lengths are those two numbers. So if I'm trying to, the overall goal of the product rule is to find out, hey, how much is the product of these two functions changing? I'm looking for the change in the f times g function. All right, well, if I want to understand multiplication, then I reach for the area model. So what I want you to now imagine is that there's some function f and some function g, and these two functions are changing over time. So let's let this side of this rectangle represent the value of f at any given moment. So as time is changing, this f segment is getting shorter and longer, yeah? And this g segment is getting shorter and longer over time as g changes. And the rectangle here, okay, the rectangle here is the area of this rectangle is just the product. So that's the value of the function at any given moment. Okay, well, what do I mean when I ask for the derivative of this? I'm asking for the change. How much is this product changing? All right, well, how much does f change, first of all? Well, in some infinitesimal small amount of time, f is going to change by some tiny bit. Let's just call it delta f. What is delta f? It's kind of just like the derivative, right? But we're being very casual now. Delta f is just the change in f in some infinitesimal amount of time. Okay, and then g also changes by some infinitesimal amount. Let's call that delta g. Now, delta f and delta g are not the same, right? If the derivative of f is big, then delta f might be very big. If the derivative of g is small, delta g might be very small. But okay, what do I get? What I get is this overall new rectangle. And this overall new rectangle is the change in the fg function. And so, switching colors here, what do we get? Well, you get these sort of three extra little rectangles, right? This is delta g, the infinitesimal change in g, times f. This is the infinitesimal change in f times g. And this is the product of the infinitesimal change in f and the infinitesimal change in g. This is actually kind of, in some ways, is a follow-up to what we did in the video with the derivative of x squared and x cubed. So actually, this should be kind of familiar. Okay, and here it is. This is the product rule. I just discovered it. This is like how they did calculus 300 years ago. The answer is that the amount by which this product function changes is just the infinitesimal change in f, in other words, the derivative of f, times g, plus the infinitesimal change in g, which is just the derivative of g, times f. And then this thing, whether you already believe this or not, this is just kind of like, that's just like going to zero. That's just like, I can skip that, because that's just like the product of two infinitesimals. So that's just like ignorable. Okay, great. This is like how Isaac Newton proved the product rule. It's the derivative of f times g plus the derivative of g times f. Okay, and we can even look at sort of a picture of this. I asked you to kind of imagine this picture, but I actually made a file which kind of shows it more directly. Yeah, it's running out of time. So we have this, here's what we have here. We have these two functions. There's a green function and there's a blue function. And the green function is a parabola, but you can change this. I'll share this file. This g function is some kind of sinusoid. And what's going on here? Well, we have this bar over here, which is simply changing the x value. So I'm changing the point on the x-axis where we're taking the derivative. So put it anywhere you want. This seems good. 2.8. Well, then you have the blue function has a certain height at that moment, and that height is in purple. So it's this purple segment, which is being copied over here. So as I change the location where I'm evaluating this function, this purple segment is changing. And then this orange segment is just the height of the green function at that moment. And that's been copied over here. And so, just like I was saying, as x changes, I have this rectangle over here in the top left-hand corner, which has one purple side and one orange side. And that rectangle is getting smaller, bigger, smaller, bigger, smaller, bigger, smaller, yeah? Okay, well, what's h? H is supposed to be kind of like an infinitely small amount of time. And I can drag h around. H is what's being changed over here. It's this little bit, right? It's this little delta x. And so the red segment here is the change in the green function given some infinitesimal amount of time. So it's basically the derivative of the green function. And that's been copied over here. And this little pink thing is the derivative of the blue function. So given some infinitesimal amount of time over here, then this change in pink, this little pink segment is the derivative of the blue function. And so now as x changes, as I change h, I can make that infinitesimal be sort of bigger and smaller. But basically what's going on here is a dynamic version of the picture I just presented in the previous slide. And so what is the overall change in the product of these two functions? It's just a big rectangle minus the little rectangle. So therefore, it's these kind of three tiny pieces. Cool? Okay. All right. This was like fine, but maybe you're thinking like this is too casual or something. Like Mr. Rose, this isn't the 17th century. This is like it really happens, right? The change in this function is x squared cosine x and 2x sine x. And then this is just like 0, basically, in relation to the others. Cool? All right. So that's like the deep way of understanding this. But mostly it's important to just be able to like do it, man. So like, what's the derivative of e to the x times x cubed? Well, it's the derivative of the first. So that's e to the x times the second, x cubed, plus the first, times the derivative of the second, which is 3x squared. Pretty easy, huh? And you can even like do some simplification and stuff. So that's like, you know, x squared e to the x plus 3. That's kind of nice if you want to. That's how it will probably like appear in the back of the book and stuff. Okay, how about this one? Do we know how to differentiate natural log? We do. So let's go. Derivative of the first is 1 over x times the second plus the first times the derivative of the second. The derivative of x to the 1/3 is 1/3 x to the negative 2/3. And in this case, there's quite a lot of sort of helpful simplification that you could do here, right? Because that's x to the 1/3 over x. So that's actually 1 over x to the 2/3. And this is ln x over 3x to the 2/3. So one sort of nice compact way of writing this final answer is this is actually just like this. So here I put in extra effort to like get a common denominator and stuff like that. Is that worth it? I don't know, sometimes, especially if you're going to do something with the derivative afterward, like find where the tangent lines are 0 or something like that. Okay, how are we doing? This is the takeaway skill besides the understanding is being able to like do these. Okay, more. Well, I want to find the derivative of a quotient. How am I going to do that? That's what I promised you, didn't I, at the beginning of this class? I said that we would learn how to differentiate 10. Well, I have 2 options right now. I can try to do a proof using the limit definition. I can try to make a whole big weird picture or something in which I interpret, you know, division. That sounds really hard and scary. Or I could just accept that there's no such thing as division, and division is just multiplication by the reciprocal. So f divided by g is really f times 1 over g. And so really quotients are just products. And so having already put all this effort into understanding and proving the product rule, let's just apply the product rule here. So that says that it's the derivative of the first, so f prime times the second, which is 1 over g, plus the first, f, times the derivative of the second. And so now I'm faced with the following problem. How do I differentiate 1 over something? Okay, and you might think you know how to do this, but you don't know how to do this, right? So are you sort of feeling this now? I need a rule for differentiating 1 over something. Okay, it's almost like what I need is a reciprocal rule. All right, let's go. What is the reciprocal rule? This is not in our book, but it should be. Everyone should have in their back pocket a technique and formula for differentiating 1 over a function that we already know the derivative of. All right, let's do it. I can't think of anything to do, so I'm going to just go back to the definition of the derivative. So this becomes the limit as h goes to 0 of 1 over gx plus h minus 1 over g of x all over h. Agree, agree? Okay, well, now what? We have a lot of skills regarding limits, so maybe it's obvious what to do next. Andrew, you're doing a lot of sign language that you think I always know, but only 30%.
Get a common denominator?
Get a common denominator, yeah. Maybe that wasn't too hard to figure out. He just went like this, and he expected me to know that that meant get a common denominator. All right, yeah, but sure, yeah, we can do that. So what do we get? We get g of x minus g of x plus h all over g of x plus h, g of x, and then that whole thing is over h. So, okay, becoming like an expert on limits and algebra and stuff. So I'm just going to do this all in one step. Follow? And now we should start to kind of see something. Do you see something? What is that numerator? You're supposed to recognize this in seconds, that numerator is basically the numerator in the definition of the derivative, except reversed, yeah? Okay, so what is everything I just circled in yellow? It's basically like the opposite of the derivative of g, essentially, right? Yeah, and so continuing this onto the next line, what I'm gonna get is negative the limit as h goes to 0 of g of x plus h minus g of x all over over h times. So what am I doing here? I'm applying the limit of a product as the product of the limits logic, and also factoring out a negative, and I'm left with this. Okay, so what is this? It's negative g prime times 1 over, that's like a g and another g. So 1 over g of x squared. All right, so here it is. The reciprocal rule says that the derivative of 1 over a known function is the opposite of the derivative of that known function over the square of that known function. Okay, well, we decided to discover and prove the reciprocal rule so that we could do the quotient rule. But before we leave this slide, is there a famous function that you can think of that is ultimately just like a reciprocal? Like what's your favorite function that's really just 1 over a better known function?
Negative exponents.
Yeah, actually, that is one example. So he says, let's see, he says, yo, Mr. Rose, you made us accept this like kind of BS argument that I should supposedly trust you when the power rule was a negative integer. So now let's let n be a positive integer. And so ultimately, you know, the fact that this rule works for negative integers is like unclear. Well, says Andrew a little bit, maybe I'm twisting his words. I can now actually prove the power rule for negative integers because x to the negative n is really just 1 over x to the n. And I know how to now differentiate 1 over a function. It's the opposite of the derivative of that function. What's the derivative of x to the n? It's nx to the n minus 1 over x to the n, you know, squared. And so that becomes negative nx to the n minus 1 over x to the 2n. And when you subtract, you get negative nx to the n minus 1 minus 2n is like negative n minus 1. And that is exactly what the product, what the power rule suggests is supposed to happen. So that's like a loose end that we just tied up. Remember, I told you to trust me on the negative integer thing? Okay, that wasn't the example I was thinking of, though. The example I was thinking of was something like secant. Because what is secant? It's really just 1 over cosine, right? And so I know how to differentiate cosine, so now I also know how to differentiate secant. It's just 1 over cosine, and then I apply the reciprocal rule. And the reciprocal rule says that the derivative of 1 over something is the opposite of the derivative of that thing. The derivative of cosine is negative sine. So, so this is the opposite of negative sine over cosine squared. Chop. And so you can leave it like that, or most people will think of that cosine as being split up into 2. And so the way people will usually give the formula for the derivative of secant is it's tan x secant x. All right, so that's a use. Those are 2 uses of the Reciprocal rule, you can also prove the derivative of cosecant this way, of course. All right, what did we do this for, however? We did this for like this spot right now, right? We did this because we wanted to know what the derivative of 1 over g is. And well, now we know. It's the opposite of the derivative of g over g squared. And so here is where I am right now with this quotient rule thing. And what people will usually do now is they'll get a common denominator by multiplying by g over g. And the sort of final quotient rule is it's the derivative of f times g minus derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay, this is what's called the quotient rule. Of course, it's in our book and stuff. So, or you can just look at the slide presentation later. It's just a rule for differentiating the quotient of two functions. And yeah, it's just the product rule and the reciprocal rule together. Okay, last couple minutes of class. Let's do, 2 examples or something. The derivative of cosine x over x cubed. Well, it's the derivative of the top, negative sine, times the bottom, x cubed, minus the top, times the derivative of the bottom, all over the bottom squared. Derivative of the top times the bottom minus top times the root of the bottom. Okay, and a lot of sort of cancellation happens here. You get negative x cubed sine minus 3x squared cosine, but then that whole thing is like over x to the 6th. And so it is possible to like rewrite this a little bit smoother. You can divide by x squared on the top and the bottom. And so you get sort of like negative x sine x plus 3 cosine x over x to the 4th. That's how you would probably see it like in the back of the book. Okay, derivative of tan. Well, once again, I can represent tan as sine over cosine. So let's go. It's the derivative of the top, which is cosine, times the bottom, another cosine, minus the top, which is sine, times the derivative of the bottom, which is negative sine, all over cosine squared. And something kind of cute happens. What is that numerator? 1. That numerator is 1. And so in fact, this whole thing is 1 over cosine squared. And in fact, the derivative of tan is therefore secant squared. Okay, going a little fast. I guess I'm not going to do this one because whatever, it's just kind of hard and annoying because you have to do like a product rule inside a quotient rule. Let's just skip to this very last thing. This is the last thing we'll do. This looks like you should use the quotient rule here, but don't use the quotient rule here. Because it's much easier to just not use the quotient rule when you don't have to. And you don't have to here because you can split this up into 3 terms. And so this is actually like 9x to the 5 halves minus 5x to the 3 halves minus x to the negative 1 half. Via exponent rules, right? And just looking at me weird. Yeah, we need to all be like experts on certain algebra background topics. Is it kind of coming back to you a little bit? Is everyone's, I think I did that right. I think that's right. And now you differentiate. So it's 45 over 2, x to the 3 halves, minus 15 halves, x to the 1 half, plus 1 half, x to the negative 3 halves. And then you're just done, or you can do some simplification, but you certainly don't have to do the quotient rule. All right, that was today's class. Kind of fast paced, kind of slow. I don't know. This was more of like a normal calculus class. We had like one thing to do. We didn't go over any homework. We posed the product rule and the quotient rule. We discovered it, we thought about it, we proved it, we did some practice problems. Homework is going to be to do a bunch more of these, and there's another million things going on Canvas. So